Stoichiometry in thermochemistry. So as you've been seeing, all the reactions are represented as equations. So for example, if we take aluminum oxide solid to give us 2 aluminum solid plus 3 by 2, 1.5 oxygen, and the delta H value, the enthalpy for this is plus 1676 kilojoule. So then you can calculate actually the amounts of energy released when you have a certain gram value of this. Why? Because in stoichiometry everything is balanced out. So as we did previously also when we did about manipulations of chemical equations, everything has to be balanced. So here this is also all balanced. You have 2 aluminum here, 2 aluminum here, 3 oxygens here, and 3 oxygens over here as well. So everything is balanced out. The mole ratios given here are 1 mole, 2 mole, 3/2 moles, and you can use that 1.5 mole, okay, easily. So those are the numbers that are given to us, and now you can calculate pretty much anything over here because delta H is the enthalpy, and the enthalpy usually we don't write as much, but it is understood that it's kilojoule per mole. Okay, that's usually how it is per 1 mole, but we don't write the mole quantity here because the moles can be different. For example, the aluminum here, the aluminum oxide is 1 mole, however aluminum is 2 moles. Okay, and that's why we don't write the mole, but otherwise it's understood that it's kilojoules per mole. Okay, but actually 2 moles of aluminum are being produced in this reaction, and similarly 1.5 moles of oxygen. So when you say that you have 1676 kilojoules being made, well, that's actually coming from 1 mole of aluminum oxide, but 2 moles of aluminum are being made from this. So I hope you understand that why we don't use the per mole, but otherwise you can easily use the mole quantity over here. Okay, so now in this case, now this is probably one of the least important parts here because in stoichiometry we don't really talk about this, is that this is endothermic reaction. I'm just going to write it, although in this case it's not so important. You just deal with the equation as it's given. Usually you don't have to manipulate anything. Okay, so let's look at a question now. So the question is, how many grams of aluminum can form when 1.000 times 10 to the power 3 kilojoule is transferred. So we're given the energy and we're asked to find the grams of aluminum, okay, over here. So the first thing we have to do, okay, first thing is to make sure equation is balanced, which it is. Okay, we just checked it, so it is balanced, but you should check it if you're doing on an exam or a homework that your equation is balanced. Second thing is, of course, your strategy. Okay, how are you going to approach this? So the strategy for this one is that you will take the energy because that's what's given to you. So always start with what is given to you. So energy is given to you, and then you will take it to the mole ratio. And what mole ratio are we talking about? We're talking about aluminum as a mole ratio because that's what's in the question. And then we'll take the mole to gram. That is our final answer because that's what the question is asking for. Okay, is how many grams. So it's asking for grams, aluminum, and the energy is given to us. Okay, and so that's our strategy. So to set up the problem becomes very easy then. The energy that's given to us is 1.000 times 10 to the power of 3 kilojoules. And now for the mole ratio is coming from the balanced equation over here. And 2 moles of aluminum will give us 1676 kilojoules. Okay, so you can use this as a conversion factor and then, you know, make sure that you keep things on the top that you need, and then convert the moles to grams. And in 1 mole of aluminum you have 26.98. This is coming from the periodic table. Okay, so from PT, from periodic table. All right, so make sure that our units are crossed out. So kilojoules, kilojoules, moles of aluminum, and we are left with grams of aluminum over here. And the final answer for this one, once you calculate, should come out to be 32.20 grams of aluminum. So what does this mean? It takes 32.20 grams of aluminum to transfer this much of energy. Okay, so that's how you would do a stoichiometric calculation. Let's do another question over here, and this question is how much energy is released during the combustion of 3.62 grams of aluminum. Now the combustion of aluminum means that you're actually taking aluminum and you're adding oxygen to that, okay, which means that the equation is reversed, okay, that's given to us, although that is a meaningless part, okay, because the only thing that does for us is it changes the number, the value of delta H, okay, the sign, but it's endothermic or exothermic. Otherwise the strategy is still the same, okay, the strategy does not change. So strategy here is grams, and why we're dealing with grams is because we're giving grams of aluminum. So grams of aluminum to mole ratio, and again mole ratio will be aluminum to the energy, and then we will go from there to the energy, okay, that is being released. So now let's go ahead and put in all the numbers. For the grams of aluminum, we have 3.62 grams of aluminum, and then for converting it into moles, okay, over here, and that is in 1 mole of aluminum we have 26.98 grams. So I'm sorry, over here I'm going to cancel this out, not mole ratio, the moles of aluminum. So convert grams to moles of aluminum, and then here it will be the mole ratio, sorry about that. So mole ratio and then the energy, okay, over here that's the mole ratio that we need here, the conversion factor. Okay, hopefully we're all caught up. Okay, so grams to moles, okay, that's what we did over here, and then from moles, now we can go from moles to kilojoules coming from the equation. So in the equation we have in 1 mole, actually in 2 moles of aluminum, 2 moles of aluminum gives us 1676 kilojoules, okay, but then this is how much energy is being given out, okay, and so how much is being absorbed, and remember for us it's going to be released, which means we will change the sign to negative, okay, at one point, because it is the amount of energy released, because once you reverse the equation you also reverse the sign, okay, so I'm doing 2 things here at one time, and so then you end up getting 224.87, which is then equivalent to 225 kilojoules, and don't forget the sign, okay, over here, because this is the amount of energy released when you combust the aluminum, okay. So try to keep it simple. If the energy is given to you, then you go for the mole ratio first in order to get the moles, and then from moles you will go to grams. If the grams are given to you, then from grams you go to moles first and then use the conversion factor. So keep it simple, okay, and just make sure your equation is balanced.